Let us take a look at the following line of code. We're going to use the sort method and sort the compensation, the total compensation, in descending order. It means that we can see the very first two total compensations here, which are the highest. So the code basically sorts the table San Francisco 2019 by total compensation in descending order. As you can see, the first two top earners are Chief Investment Officer and Managing Director with total compensation on the last column. Now the question is, suppose the parameter in which we are interested is the median of the total compensations. Since we have all the data from the population, we could simply calculate the parameter. So let us calculate the population median. We're going to use the percentile function. The 50th percentile of the total compensation. So the code percentile 50 San Francisco 2019 column total compensation basically calculates the 50th percentile or the median of the total compensation column, which represents the midpoint value of the total compensation. So the result is going to be 135,747. This is the median total compensation of all the employees, which were $135,747. By using the median rather than the mean, we reduce the influence of outliers like the Chief Investment Officer and Managing Director with their much higher compensation. It gives us a better sense of typical compensation. A random sample and an estimate. So let us draw a sample of 500 employees at random without replacement and let the median total compensation of the sampled employees serve as our estimate of the parameter. We're going to take a look at our histogram. On the horizontal line, you're going to have your total compensation. And on the vertical line, you have percent per unit. The line of code here basically draws a sample of 500 employees from the San Francisco 2019 table without replacement, meaning that each selected employee appears only once in the sample. Now let us estimate the median. We're going to use the percentile function. And it calculates the 50th percentile or the median of the total compensation. This is $136,835. The sample size is large. By the law of averages, the distribution of the sample is similar to that of population. So the sample median is quite comparable to population median, though of course it's not exactly the same. So now we have one estimate of the population parameter. But what if we had another sample taken from the population? Would we get a different estimation? We would like to be able to quantify the amount by which the estimate could vary across samples. That measure the variability, and it helps us measure how accurately we can estimate the parameter itself. Well, to see how different the estimate would be if the sample had come out differently, it could just draw another sample from the population. But the question is, what if population is not available anymore, as we discussed at the beginning of this lecture? Our goal is to mimic real life in which we won't have all the population data at hand. So in that case, we're going to use Bootstrap method. Somehow, we have to get another random sample without sampling again from the population itself. This is the method of bootstrapping, or resampling from the sample. We have a large random sample from the population. As we know, a large random sample is likely to resemble the population from which it is taken. This observation basically helps data scientists to lift themselves up by their own bootstraps. The sample procedure can then be replicated by sampling from the same sample. Here are the steps for the bootstrap method for generating another random sample that resembles the population. First of all, treat the original sample as if it were the population. Next, draw from the sample at random with replacement the same number of times as their original sample size. Very good. It's important to resample the same number of times as the original sample size. What's the reason behind it? The reason is that the variability of an estimate depends on the size of the sample. Since our original sample consisted of 500 employees, our sample median was based on 500 values. To see how different this sample could have been, we have to compare it to the median of other samples of size 500. If we draw 500 times at random without replacement from our sample of size 500, we would just get the same sample back. By drawing with replacement, we create the possibility for the new samples to be different from the original sample, because some employees might be drawn more than once and others basically not drawn at all. Perfect. So why the bootstrap method work? Why this is a good idea? By the law of averages, the distribution of the original sample is likely to resemble the population, and the distributions of all the resamples are likely to resemble the original sample. So the distributions of all the resamples are likely to be resemble the population as well. So we have a population. Suppose this is the behavior of your population. And as you can see, it is skewed to the right-hand side. Now, we're going to take a sample. And then from that sample, we're going to start resampling. They're just possible visualization of resampling. And as you can see, the behavior of the histogram or visualizations are like this on the right-hand side. So we can use simulation to do that. So what's a resampled median? Recall that the sample method draws rows from a table with replacement by default. And when it's used without specifying a sample size, by default, the sample size equals the number of rows of the table. That's perfect for Bootstrap. Here is one new sample drawn from the original sample, and the corresponding sample median can be calculated. For example, let us take a look at resample 1. In this case, the line of code here basically draws a new sample that we call resample 1 from the our sample table. The sample method by default samples with replacement. This means that any employee can be selected multiple times, and the sample size will be equal to the size of our sample, which is 500 employees in this case. We can take another sample. Later on, we're going to write the line of code. But in this case, similar to before, the code creates a histogram for us. And in that histogram, we're going to use the total compensation and use the same bins as before. Let us take a look at resampled median. We're going to use percentile function, and we're going to take a look at the median here. 50 represents the 50th percentile or the median. The value is going to be $141,793. This is the resampled median. So we can repeat this process. By resampling again and again, we can get many such estimates and an empirical distribution of the estimates. We can take a look at resample 2, resampling again. And in that case, what do we have? We have the median of the second resample, which is $135,880. This is another estimate of population median. We can also collect this code and define a function, one bootstrap median, that returns one bootstrap median of total compensation based on bootstrapping the original random sample that we call one sample. We define our function as usual. This function resample from the original sample and calculate the median of the total compensation for the resampled data and return the bootstrap median. Each time this function is called, it will provide a new estimate for the population median based on the bootstrap resampling method. You can also run the cell below a few times to see how the bootstrap median will be different. Calling the function multiple times will give you different bootstrapped median. So the value that I see here might be different from the value that you run your line of code on your end. Perfect. Bootstrap empirical distribution of the sample median. We can now repeat the bootstrap process multiple times by running a for loop. In each iteration, we will call the function one bootstrap median to basically generate one value of the bootstrapped median based on our original sample, which is our sample. Then we're going to append the bootstrap median to the collection of our array. We're going to do 5,000 repetition. So it might be a little bit slow. Please be patient. Set the number of repetition to be 5,000. This variable specifies the number of bootstrap samples you want to draw. Set it to be 5,000 in this case, and then bootstrap underscore medians. Basically, it's an empty array to store the bootstrap median values as they are computed in the next line. Now, for loop for I in np.arange, we pass in the number of repetition, which is 5,000 times. The median is calculated and it appends to the previous values. Please note that np append basically returns a new array with the new value added to it, which can be inefficient for large iterations. However, this approach is straightforward for learning purposes. So basically, let's take a look at our histogram. So in our histogram, as you can see, you have a green dot. The green dot is the population parameter. It is the median of the entire population, which is what we are trying to estimate. In this example, we happen to know its value, but we didn't use it in the bootstrap process. Now the question is, do the estimates capture the true population parameter? How often does the empirical histogram of the resampled medians sit firmly over the green dot and not just brush the dot with its tails or not cover it at all? To answer this question, we must define sit firmly. Suppose we take that as the middle 95% of the resampled medians containing the green dot. So now we are switching to the topic of confidence interval. Here are the two ends of the middle 95% interval of resampled medians. Let us set the left endpoint and set the right endpoint. The percentile function, it passes in 2.5, and it basically calculates the 2.5th percentile of the bootstrap medians array, which is representing the lower bound on the left tail. So basically you have $129,524. With the same process, we can define the right endpoint. Our goal is to capture the true population parameter in this case. For the right endpoint, we look at the 97.5th percentile and using bootstrap median array, and it happens to be $143,446. The population median, which we previously calculated as $135,747, is confirmed to fall between the values of left and right endpoint. This indicates that the population median is within the range of the middle 95% of the resampled medians, demonstrating the bootstrap estimate are capturing the true population parameter. So basically, we can say that the population median of $135,747 is between these two numbers, and the interval and the population median are shown on the histogram below. So let us take a look at our histogram. The green dot representing the population parameter. Indicating that it's located in 95th percent in the 95% confidence interval for our population parameter. To see how frequently the interval contains the parameter, we have to run the entire process over and over again. Specifically, we will replicate the following process 100 times. Draw an original random sample of size 500 from the population. Carry out 5,000 replications of the bootstrap process and generate the middle 95% interval of resampled medians. We'll end up with 100 intervals and count how many of them basically contain the population median. Remember that the statistical theory of the bootstrap say that the number should be around 95. It may be in the low 90s or high 90s, but we don't expect it to be much farther off 95 than that. So take a look at the visualization. We'll start by writing a function bootstrap median that takes two arguments, the name of the table containing the original random sample and the number of bootstrap samples to draw. It returns an array of bootstrap medians, one from each bootstrap sample. Let's define our function. The line defines a function named bootstrap underscore median, takes two arguments or parameters, the original sample, that is the data set from which bootstrapping will be performed, specifically containing a column calling total compensation. That was our purpose, as you remember. And the second argument is the number of repetition, which specify how many bootstrap samples will be generated. We are creating an empty array named the medians to store the median values from each bootstrap sample. We're going to use a for loop as before that iterates number of repetition, which is in this case 5,000 times. In each iteration, the following happens. It draws a bootstrap sample. So as before, we're going to append it to the previous data. And then to calculate the median from the current bootstrap sample, it's appended to the array that we defined at the beginning. Now, we're going to write a for loop that calls this function 100 times and collects the middle 95% of the bootstrap medians each time. The cell below takes several minutes to run because it has to perform 100 replications of sample 500 times at random from the table and generating 5,000 bootstrap samples. So please be patient. For those of you who are interested in the breakdown of the code, you have all the information here, but mainly we are interested in looking at the visualization and analyze it. So we are taking two empty arrays, left end and right end, that are created to store the lower and upper bounds of the confidence interval from each iteration of the simulation. Then you have a for loop. This for loop runs 100 times allowing the entire bootstrapping process to be replicated to generate a robust estimate of the median and its confidence interval. You have a random sample of 500 employees and with replacement, which is false, indicates that each employee can only be selected once for this sample. Then you have your bootstrap median. This function basically calculates the median of the sample for you. For each of the 100 replications of the entire process, we get one interval of estimate of the median. So if you look at the intervals, basically you have left endpoint to right endpoint, left endpoint to right endpoint. And if you visualize this, you can basically find a good intervals that contains the parameter we are trying to estimate. Typically, the parameter is unknown, but in this section, for the sake of learning, we happen to know what the parameter is. Now, if you look at the population median, it is 135,747. And the question is, how many of these 100 intervals basically contain the true population median? That's the number of intervals where the left endpoint and the right endpoint basically captures this number. You basically have 93 intervals. The number of intervals is 93. Remember that it's hard to show you all the intervals on the horizontal axis as they have large overlaps, but the graphic below shows each interval on the same axis by stacking them vertically. The vertical axis is simply the number of replication from which the interval was generated. The green line is where the parameter is. As you remember, this was a population median. It has a fixed position since the parameter is fixed. Good intervals cover the parameter. There are approximately 95 of these. If an interval doesn't cover the parameter, we're going to ignore it. The dots are the ones where you can see daylight around the green line. There are very few of them, about 5 out of 100. But they exist, we can't ignore them. Any method based on sampling has the possibility of being off. And the beauty of methods based on random sampling is that we can quantify how often they are likely to be off. To summarize what the simulation shows, suppose you're estimating the population median by the following process. Draw a large random sample from the population. Bootstrap your random sample and get an estimate from the new random sample. Repeat the above bootstrap step 1,000 of times and get 1,000 of estimates. Pick off the middle 95% interval of all of the estimates. That basically gives you one interval of estimates. If 99 other people repeat the entire process, starting with a new random sample each time, then you'll end up with 100 such intervals. About 95 of these 100 intervals will contain the population parameter. In other words, this process of estimation captures the parameter about 95% of times, and you can replace 95% by a different value as long as it is not 100. Suppose you replace 95% by 80% and keep the sample size fixed at 500. Then your interval of estimate will be shorter than those we simulated before. Why is that? Because the middle 80% is a smaller range than the middle 95%. If you keep repeating this process, only about 80% of your intervals will contain the parameter